Are you ready to master the future of AI? Introducing the NCA-GENL, NVIDIA-Certified Generative AI LLMs Specialization, your fast track into the world of large language models, prompt engineering, and cutting-edge AI tools built by NVIDIA. In this course, you'll go from the core foundations of machine learning to advanced topics like transformer architecture, instruction tuning, and alignment techniques used in real-world systems like GPT, BERT, and T5. You'll get hands-on experience with NVIDIA NeMo, Triton Inference Server, TensorRT, and the full LLM toolchain, skills that will not only help you ace the NCA-GENL certification, but also make you stand out in the AI job market. We've packed this course with clear explanations, practical labs, mock tests, and insider tips to help you build confidence and skill fast, whether you're a student, an aspiring AI engineer, or a professional looking to upskill. This course is your launchpad into generative AI. No PhD required, no fluff, just what you need to learn, practice, and get certified. Enroll now and unlock your career in generative AI with NVIDIA's official certification. Let's build the future together. This session introduces the NVIDIA-Certified Associate, Generative AI and LLMs, NCA-GENL exam. You'll understand the purpose of the certification, the audience it's designed for, why this credential matters in the AI job market, the broader goals of NVIDIA's certification ecosystem. By the end, you'll have a clear picture of what the certification represents and how it aligns with your Gen AI learning path. The NCA-GENL, or NVIDIA Certified Associate Generative AI and LLMs, is an entry-level industry credential. It verifies your understanding of generative AI concepts, foundational machine learning, and practical tools like NeMo, Triton, and TensorRT. Whether you're a developer, data scientist, or product strategist, this certification signals that you can responsibly and effectively work with large language models in the NVIDIA ecosystem. This certification is designed for a wide range of professionals. AI engineers and DevOps specialists benefit by showcasing proficiency in deploying and optimizing LLMs. Product managers and data analysts gain credibility in leading Gen AI projects. It's also a valuable on-ramp for those entering the AI space, especially where NVIDIA's stack is involved. Certifications today are more than badges, they're signals to employers. The NCA-GENL carries NVIDIA's name, which adds weight in industry settings. It's particularly useful if you work on or aspire to work on AI deployments involving large-scale inference, cloud integration, or LLM-backed applications. It also acts as a stepping stone toward deeper specializations in NVIDIA's certification ladder. Earning the NCA-GENL certification shows that you understand how LLMs work under the hood. You'll demonstrate fluency in designing effective prompts and knowledge of how to evaluate model outputs for quality and bias. More importantly, you'll show employers that you can integrate NVIDIA technologies into the Gen AI development lifecycle, from model training to deployment. This session is all about understanding how the NCA-GENL certification exam is structured, what to expect before, during, and after the test. We'll break down the number and type of questions, time limits, scoring model, test environment, and important logistical considerations. Whether you're new to certification exams or experienced in online proctor testing, this section will help you build confidence in your exam readiness and eliminate any surprises on test day. The NCA-GENL exam consists of 50 to 60 multiple-choice questions. You'll have 60 minutes to complete the entire exam, which means you'll need to manage your time wisely, aiming for roughly 1 minute per question. The questions are not purely factual. They often revolve around scenarios involving LLMs, prompting, and NVIDIA tools. For example, you might be asked which tool would optimize inference latency for a given deployment case. It's a closed book, single attempt exam, so preparation is key. Expect a mix of conceptual and applied questions. Some will test your understanding of attention mechanisms or transformer structure. Others will ask you to reason through prompt design decisions or model deployment choices. You'll also see questions that relate directly to NVIDIA's ecosystem. For instance, when to use NeMo for training or Triton for inference. Many questions are framed in real-world development or deployment scenarios, so practical thinking matters as much as theoretical knowledge. The exam is administered entirely online through a proctoring platform. Before starting, you'll need to verify your identity with a government-issued photo ID and set up your testing environment according to strict guidelines, usually with a webcam and a clean workspace. You'll also use a secure browser that blocks access to other tabs or programs. A dropped internet connection could jeopardize your session, so be sure to test your setup in advance and have backup connectivity if possible. NVIDIA doesn't publicly disclose the exact passing score, but most examinees report that you'll need somewhere between 70 and 80% accuracy to pass. All questions are single best answer, with no partial credit for multiple choice items. That means you either get the question right or wrong, so elimination and educated guessing are vital skills. In most cases, your results will appear immediately upon submission, though some candidates have reported a short delay of a few hours. Once you pass the exam, your certification is valid for 2 years. If you don't pass on your first attempt, you may need to wait a set period, often 14 days, before retaking, and you'll need to pay again. When you do succeed, you'll receive a printable PDF certificate and a digital badge issued through Credly, which you can add to your LinkedIn profile or resume. NVIDIA also links this credential to your ecosystem ID, which helps you stand out in their community and partner networks. In this session, we'll walk through the cost of taking the NCA-GENL exam and how to register. You'll learn how much the certification typically costs, whether discounts are available, and how the exam fits into broader NVIDIA learning bundles. We'll also go step by step through the registration process, from selecting your exam provider to receiving your scheduling link. By the end, you'll know exactly what to expect when it comes to investing both your time and money into this credential. The base cost of the NCA-GENL certification exam typically falls between $125 and $135 in US dollars. This includes one full attempt with proctoring and certification issuance if you pass. If you fail, you'll need to pay the full amount again to retake it. There are no free retries. However, NVIDIA often bundles the exam with their Deep Learning Institute DLI courses. These bundles can offer better value, especially if you're planning to use their learning path as your prep strategy. If you're cost conscious, there are several ways to reduce your expense. The most common approach is to purchase a bundled DLI learning path, which includes the exam voucher at a reduced rate. Occasionally, NVIDIA releases promotional codes through its newsletter or during events. Academic institutions and enterprise teams may qualify for bulk discounts, and students might be eligible for lower rates by registering through educational programs or NVIDIA-affiliated platforms.
To register, start by visiting the official NVIDIA certification portal. Locate the NCA-GENL certification and click Enroll. You'll be asked to choose a delivery partner. NVIDIA typically works with platforms like Pearson VUE or PSI. Once you select a date and pay online, you'll receive an email with a scheduling link and instructions for test day. It's recommended to schedule your exam at least 1 week in advance to ensure your ideal time slot is available.
Once you've paid, you can usually schedule your exam at a time that works best for you, day or night, any day of the week. Rescheduling is allowed up to 24 hours before your test slot, but failing to show up or being late will result in a forfeited attempt. Be mindful of expiration dates if you received your voucher as part of a bundle. Most vouchers are valid for 6 to 12 months, so don't wait too long before booking your date. In this session, we'll break down the core skills and tools covered by the NCA-GENL exam. You'll learn what technical topics make up the exam blueprint, what NVIDIA-specific technologies you'll need to understand, and how the questions are distributed across different domains. This includes everything from transformer theory and prompt engineering to using NeMo, Triton, and Rapids. By the end of this session, you'll know exactly what knowledge areas to focus on in your preparation. The NCA-GENL exam is structured around a few foundational skill domains. First, you'll need a working understanding of machine learning concepts, including neural network training, Next, you'll be tested on transformer architecture and the mechanics behind large language models. Prompt design is a core area as well. Expect several questions on how to craft, evaluate, and refine prompts. Finally, you'll be asked to reason through scenarios involving experimentation, metric interpretation, and model behavior in the wild. This isn't just a theory test, it's also about tools. NVIDIA expects you to be familiar with their Gen AI stack. NeMo is their go-to framework for training and fine-tuning large language models. Triton Inference Server handles real-time model serving and optimization. Rapids includes libraries like cuDF and cuML for high-speed data processing using GPUs. You'll also see questions involving TensorRT and OnX, which help with converting and optimizing models for inference on NVIDIA hardware. While NVIDIA doesn't provide an official breakdown of question weights, we can approximate based on exam taker reports and prep guides. About 30% of the exam touches on core machine learning and neural network concepts. Roughly 24% deals with software development and deployment practices, particularly with NVIDIA tools. Experimentation and evaluation make up 10 to 14%. And finally, about 25 to 30% of the exam is dedicated to prompt engineering, alignment, and Gen AI safety topics. One of the most important things to understand is that this exam is not about memorizing definitions or theoretical jargon. Most questions are scenario-based. You'll be given a problem and asked to choose the best tool, configuration, or prompt strategy. You may be given a suboptimal model pipeline and asked how to improve inference speed or reduce hallucinations. The exam values decision-making and practical reasoning over rote learning. This session is about how to study smart, not just hard. We'll explore how to structure your preparation over 4 to 6 weeks, combining theory, practice, and tools. You'll learn how to build momentum, avoid common pitfalls, and keep a healthy mindset through the process. Whether you're coming from an engineering, data science, or product background, this plan will help you stay on track and make your preparation more efficient and effective. For most learners, preparing for the NCA-GENL exam takes around 4 to 6 weeks, assuming you can dedicate 6 to 10 hours per week. If you already have a strong background in machine learning or large language models, you might be able to prepare faster. But consistency matters more than cramming. Spreading your study time across multiple short sessions per week, especially with hands-on labs and review, leads to better retention and confidence than binge studying right before the exam. When building your study plan, prioritize understanding how LLMs are structured and how prompts are engineered. These topics show up frequently in the exam and are foundational to Gen AI workflows. Then, shift focus to NVIDIA's specific tools, especially NeMo for training, Triton for deployment, and Rapids for GPU-accelerated data processing. Don't forget evaluation metrics like Blue, Rouge, and Perplexity. And most importantly, train yourself to reason through scenarios rather than just memorize answers. Each week, aim to balance 3 kinds of activities: learning new material, applying it through hands-on tools, and reviewing what you've covered. A good daily rhythm might include 1 day of reading, 1 day of experimenting with NeMo or Triton, and 1 day of reviewing questions or taking a mini quiz. Save the last week for mock exams that simulate real testing conditions. These practice exams help identify weak spots and build the confidence you need for the actual test. Approach the NCA-GENL exam with a practical mindset. It's not about being perfect. It's about being proficient. You're not expected to know every answer, and you will get some questions wrong. That's okay. The goal is to understand the core ideas, make educated decisions, and apply your skills in realistic Gen AI scenarios. Let your mistakes during practice guide you, not discourage you. Stay focused, keep it simple, and remind yourself why you're pursuing this in the first place. In this session, we explore the 3 primary learning paradigms in machine learning: supervised, unsupervised, and reinforcement learning. These paradigms define how a model learns from data, and understanding them is crucial for working with generative AI systems. We'll cover how each type works, what kinds of problems they solve, and how they relate to LLM development. By the end of this session, you'll be able to distinguish these approaches and understand where they appear in practice, especially in Gen AI contexts. A learning paradigm is essentially a strategy for how a machine learning model learns from data. The paradigm you choose depends on the kind of data you have and the problem you're trying to solve. In modern AI, we commonly use three major paradigms: supervised learning, unsupervised learning, and reinforcement learning. These approaches guide how models are trained, what kind of feedback they receive, and how they adjust over time. Understanding these is foundational to everything else you'll learn about generative AI and LLMs. Supervised learning involves training a model on input data that has corresponding correct answers, called labels. For instance, you might train a model on product reviews and their associated star ratings, teaching it to predict ratings from new reviews. This approach is widely used for classification and regression tasks, and it also plays a key role in fine-tuning large language models, where labeled prompts and ideal responses guide the model's behavior. Unsupervised learning is all about discovering patterns in unlabeled data. Unlike supervised learning, there are no correct answers provided during training. Instead, the model learns to group similar items, identify structure, or reduce complexity. It's used in clustering, anomaly detection, and more. Interestingly, the initial stages of LLM pre-training, like masked language modeling in BERT or next token prediction in GPT, can be considered forms of unsupervised learning because they don't rely on explicit external labels. Reinforcement learning takes a different approach. Here, an agent learns by interacting with an environment and receiving feedback in the form of rewards or penalties. Over time, it learns a strategy, called a policy, that maximizes reward. This is how AI systems have mastered games like Go and StarCraft in the context of LLMs. Reinforcement learning with human feedback, or RLHF, is used to align models with human preferences by guiding them toward more helpful or safe outputs. Each paradigm serves a unique purpose. If you have clean, labeled data and a clear output goal, supervised learning is ideal. If you're trying to find hidden structure or groupings in raw data, unsupervised learning is a better fit. Reinforcement learning is powerful when actions affect future outcomes, such as in games, autonomous systems, or LLM alignment tasks. In practice, many AI pipelines combine these paradigms. For example, starting with unsupervised pre-training, followed by supervised fine-tuning, and ending with RLHF. In this session, we explore the anatomy of a neural network, the computational engine behind most modern machine learning models, including LLMs. You'll learn about the basic building blocks like neurons, layers, activation functions, and parameters. We'll also cover different types of architectures, including feed-forward, convolutional, and recurrent networks, and how they relate to transformers. Understanding these structures will give you a deeper grasp of how large models like GPT or BERT process and generate language. At its core, a neural network is a series of interconnected nodes called neurons that work together to detect patterns and relationships in data. Each neuron receives inputs, applies a mathematical function, and passes the result to the next layer. Over time, the network learns by adjusting internal weights based on the errors it makes. While inspired by biological neurons, these systems are purely mathematical. Neural networks are the foundational technology behind large language models and nearly all deep learning systems in use today. Neural networks are made up of several layers. The input layer takes in raw features, like token embeddings in the case of language models. Hidden layers, which can range from just a few to hundreds, perform transformations on that input using mathematical operations. The final output layer generates predictions. What makes this structure powerful are the trainable weights and biases between layers, and the activation functions that introduce nonlinear behavior. This enables neural networks to learn complex, non-obvious patterns in data. There are several types of neural network architectures, each suited to different kinds of data. Feed-forward networks are the simplest. They process data in one direction with no memory of past inputs. Convolutional networks are specialized for spatial data like images, using filters to detect patterns. Recurrent networks, or RNNs, are designed for sequential data like text or time series because they can retain memory from previous inputs. However, RNNs struggle with long sequences. This led to the development of transformers, which handle long-range dependencies much better. Activation functions are what make neural networks truly powerful. Without them, the entire network would behave like a basic linear equation, unable to model the complex, non-linear relationships found in real-world data. ReLU, or rectified linear unit, is the most common activation due to its simplicity and speed. Other functions, like sigmoid and tan, are still used in specific contexts. These functions are applied at every neuron in the hidden layers and play a critical role in how the network adapts and improves during training. Even though large language models like GPT-4 or BERT seem complex, they're still built from the same neural network fundamentals we've just explored. These models consist of many stacked layers of computation. Transformers, in particular, replaced recurrence with a more powerful mechanism, attention. But underneath, they still depend on the same core ingredients: layers, weights, activations, and loss functions. Once you understand these basics, you're well equipped to grasp how LLMs function at scale. In this session, we'll dive into how neural networks are trained and optimized. You'll learn how models learn from data by minimizing a loss function through iterative updates. We'll explain key concepts like gradient descent, the role of learning rate, and how backpropagation works behind the scenes. You'll also see how choices in optimization affect performance and stability, especially when working with large-scale models like LLMs. Understanding this process is critical to evaluating, debugging, and improving any deep learning system. Training a neural network involves repeating the same process over and over. You start by feeding input data into the model. The network makes a prediction, and you compute the error, called the loss, by comparing that prediction to the correct output. Then, using calculus, you compute how much each parameter contributed to that error. These gradients tell the model how to adjust its internal weights to reduce the loss next time. This loop, forward pass, loss calculation, gradient computation, and update, runs across many passes over the dataset, known as epochs. Gradient descent is the optimization algorithm at the heart of neural network training. It works by adjusting each weight in the network in the direction that most reduces the loss. This direction is given by the gradient, which measures the slope or steepness of the loss surface. By taking small steps, controlled by a parameter called the learning rate, the model moves closer to the ideal set of weights. If the learning rate is too small, training is slow. If it's too large, the model might overshoot and never converge. Backpropagation is the algorithm that makes gradient descent efficient, especially for deep networks. When a prediction is wrong, the model calculates the error and then works backward through the network to figure out which parameters were responsible. It uses the chain rule of calculus to do this in a structured way, layer by layer. This allows every single parameter in the network to be updated based on how much it contributed to the error, even in very deep models like transformers. While vanilla gradient descent works, it's often too slow or unstable for modern use cases. That's why we use optimized versions like SGD with momentum, Atom, or RMS prop. These algorithms automatically adjust the learning rate for each parameter based on how frequently it changes, which speeds up convergence and reduces oscillations. Learning rate schedules can also be used to fine-tune the optimization process over time. Additionally, the size of the data batches you use in training affects both memory usage and how smooth your updates are. Training large language models is fundamentally the same process, but at a completely different scale. Instead of a few thousand weights, LLMs like GPT-3 have hundreds of billions. They require data centers filled with GPUs and advanced strategies like pipeline and data parallelism. To manage memory and speed, training often uses mixed precision, combining 16-bit and 32-bit floating point operations. Every decision around optimization, like batch size, learning rate decay, or regularization, has a massive impact on both training time and final model performance. In this session, we explore one of the biggest challenges in machine learning, ensuring that a model performs well not just on training data, but also on new, unseen data. We'll define overfitting, underfitting, and the concept of generalization. You'll learn how to detect when your model is memorizing rather than learning, and we'll explore regularization techniques used to prevent this. These concepts are essential whether you're training a simple classifier or fine-tuning a massive LLM. Overfitting happens when a model learns the training data too well, so well that it memorizes noise and outliers instead of discovering general patterns. This results in high accuracy on the training set, but poor performance on new data. You can often spot overfitting when you see the training loss continuing to drop, but the validation loss starts rising. It's especially common in deep neural networks and large models with millions of parameters, like those used in generative AI. Underfitting is the opposite problem. It happens when the model is too simple or not trained long enough to learn the important patterns in the data. It makes poor predictions even on the training set. You'll see both training and validation loss remain high. Solutions include using a more complex model, engineering better features, or allowing more time for training. In the LLM world, this might occur if you try to fine-tune a model on too little data or with an overly constrained architecture. Generalization is what we ultimately care about. It means the model has learned patterns that apply not just to the training set, but to real-world data it hasn't seen before. We measure this using a validation or test set. A well-generalized model performs consistently across both sets. The challenge is finding the right balance, enough model capacity to learn, but not so much that it memorizes. Generalization is especially critical for LLMs deployed in dynamic environments with unpredictable inputs. To prevent overfitting, we use regularization techniques, ways to constrain the model during training so it focuses on essential patterns. Dropout, for instance, randomly disables parts of the network during training, forcing it to learn redundantly. L1 and L2 regularization penalize overly large weights. Early stopping ends training as soon as validation performance starts to decline. And data augmentation expands your dataset to promote more robust learning. These tools are standard practice in both academic ML and industry-level Gen AI pipelines. In large language models, regularization takes on a slightly different form. Techniques like weight decay and label smoothing help improve generalization during pre-training. Gradient clipping is used to prevent extremely large updates that could destabilize training, especially in deep models. Dropout is often applied within transformer attention blocks to prevent overfitting in the attention maps themselves. Some models even use token dropout to mask parts of the input during training. These strategies allow us to scale learning while keeping models from overfitting. In this session, we'll explore how to evaluate whether a model is performing well. You'll learn about the most commonly used metrics in classification and regression tasks, such as accuracy, precision, recall, F1 score, and loss. We'll also discuss how these metrics apply to LLMs, where evaluation involves not just correctness, but also fluency, relevance, and safety. By the end of this session, you'll be able to interpret evaluation outputs and choose the right metric for the task at hand. Evaluating your model is just as important as training it. A high training accuracy doesn't mean the model will perform well in the real world. Evaluation metrics help you detect problems, compare models, and decide whether an update actually improves performance. In regulated or high-stakes domains like finance, healthcare, or compliance-driven applications, knowing exactly how your model performs and on what kinds of inputs is mission critical. In classification tasks, accuracy is the simplest metric. It measures how many predictions the model got right. But accuracy alone can be misleading, especially with imbalanced datasets. That's where precision and recall come in. Precision tells you how many of the predicted positives were actually correct, while recall measures how many of the actual positives the model successfully captured. F1 score combines both into one number. balancing the trade-off between false positives and false negatives. When your model outputs a continuous value, like predicting prices or ratings, you'll use regression metrics. Mean squared error penalizes large mistakes heavily, which can help with stability, but also makes the model sensitive to outliers. Mean absolute error is simpler and more interpretable. During training, the loss function is the metric being minimized. But during evaluation, you might report several metrics depending on what matters most for your use case. Evaluating large language models presents unique challenges. Unlike classification or regression, LLMs generate open-ended text, so correctness isn't always binary. Common automated metrics include BLUE and ROUGE, which compare model output to reference texts using overlap scores. Perplexity measures how surprised the model is by the next token. Lower is better. Still, many LLM evaluations require human judgment, especially when it comes to tone, coherence, or how well the response aligns with user intent. Choosing the right metric depends on your objective. For medical diagnoses, you might prioritize recall to ensure you catch all positives. In spam detection, precision might matter more to avoid flagging legitimate content. In Gen AI, you'll often need both automated and manual evaluation. Metrics like BLUE and Perplexity are useful, but human-in-the-loop reviews ensure responses are truly helpful, appropriate, and safe. Your evaluation strategy should always reflect the real-world impact your model has on users. In this session, we'll explore the concept of attention in neural networks, one of the most transformative ideas in modern AI. You'll learn what attention mechanisms are, how self-attention works, and why multi-head attention is used in transformer models. These ideas underpin the entire transformer architecture and are essential to understanding how LLMs like GPT, BERT, and T5 process text. By the end, you'll have a clear mental model of how attention allows language models to focus on relevant parts of input sequences, and why it replaced older architectures like RNNs. Attention is the ability of a neural network to focus on the most relevant parts of an input sequence. Instead of treating each token equally, the model assigns a weight or attention score to every word in the input based on how important it is for generating the output. This idea first emerged in translation models, but soon revolutionized all of NLP. Attention lets the model dynamically prioritize certain tokens during computation, enabling it to handle context and nuance far better than older architectures like RNNs. Self-attention is the foundation of transformer models. In self-attention, each token in a sentence looks at all other tokens, including itself, to determine which are most relevant to understanding its meaning. This is done using three components: queries, keys, and values. These vectors are used to compute attention scores that determine how much influence each token should have on the output. The result is a weighted sum that allows the model to gather contextual information dynamically at each layer. The magic of attention lies in the interaction between queries, keys, and values. Think of the query as a question. What should I focus on? Each token in the sequence provides a key, its description or identity. The model compares each query to all keys using a dot product to compute attention scores. These scores are then applied to the values, which represent the actual content being passed along. This QKV process allows each token to dynamically attend to the most relevant information in the sequence. Instead of using a single attention head, transformers use multi-head attention. This means the model runs several attention computations in parallel, each one learning a different way to interpret the sentence. One head might focus on grammatical structure, while another learns word meaning or positional relationships. These heads are then combined and passed through a linear layer. Multi-head attention allows the model to capture richer, more nuanced representations at every level of the transformer. Before attention, models like RNNs and LSTMs processed input sequentially, one token at a time, which made training slow and limited their ability to capture long-term dependencies. Attention eliminated the need for recurrence by allowing every token to interact with every other token simultaneously. This not only made training massively parallelizable, but also improved the model's ability to understand context, structure, and meaning across long texts. Today, attention is the cornerstone of every major LLM architecture from GPT and BERT to T5 and beyond. In this session, we'll look at how transformers encode positional information since they lack the built-in sequential nature of RNNs. You'll learn how positional encoding allows transformers to understand word order, and we'll break down the structure of a transformer block, including key components like layer normalization, feed-forward layers, and residual connections. These mechanisms make up the repeating building blocks that scale up to form massive models like GPT-4 and T5. Mastering this structure is key to understanding how transformers operate layer by layer. Transformers revolutionized NLP by eliminating recurrence, allowing for parallel computation. But this came at a cost. Unlike RNNs, transformers don't naturally know the order of tokens. To compensate, they use positional encoding, which injects information about token positions directly into their input embeddings. This enables the model to distinguish between the cat sat on the mat and the mat sat on the cat. Without positional encoding, the transformer would treat both as having the same meaning. One common form of positional encoding uses sinusoidal functions. Sine and cosine waves of varying frequencies are added to each token's embedding based on its position in the sequence. This creates a unique, fixed pattern for every position, one that preserves both the identity and order of each token. The beauty of this approach is that it allows the model to generalize to sequence lengths it hasn't seen during training, because the mathematical structure of the encoding is continuous and interpretable. Some models, including BERT and GPT, use learned positional embeddings instead of fixed sinusoidal ones. In this method, each position in the input has an associated vector that is updated during training, just like word embeddings. This approach is more flexible and allows the model to adapt its sense of position based on the task. However, it can be less interpretable, and the model may struggle with very long sequences if it hasn't seen similar lengths during training. Each transformer block consists of a few standard components that repeat across layers. First, there's the multi-head self-attention mechanism we covered earlier. Then, the output passes through a residual connection and layer normalization. This helps stabilize training and preserve information. After that, it goes through a feed-forward network, which adds nonlinearity and depth to the representation. Finally, another add and norm step is applied. This architecture is repeated dozens or even hundreds of times in modern LLMs, depending on model size. Transformers are built by stacking multiple identical blocks, each containing attention, normalization, and feed-forward layers. The number of blocks determines the depth of the model. Increasing the number of attention heads or neurons increases the width. Together, depth and width determine the model's overall capacity. Despite their simplicity, these repeating blocks scale beautifully, enabling architectures like GPT-4, which contains hundreds of layers and billions of parameters, all relying on the same foundational structure. In this session, we'll compare two fundamental transformer architectures, encoder-decoder and decoder-only. You'll learn how information flows through each design, the types of tasks each is suited for, and how models like BERT, GPT, and T5 are built on these principles. Understanding this distinction helps clarify why some models are better at generation, while others excel at understanding or classification. By the end, you'll be able to identify which architecture fits a given use case and how they differ in both design and application. Transformer models typically fall into one of three architectural families: encoder-only, decoder-only, and encoder-decoder. Encoder-decoder is the original full transformer architecture introduced in the 2017 Attention is All You Need paper. Decoder-only models focus on generating text from left to right, while encoder-only models are optimized for understanding text. The type of architecture determines how data is processed, what kind of training objectives are used, and which tasks the model performs best on. In the encoder-decoder setup, the encoder reads the full input, such as a source sentence in English, and transforms it into a dense representation. The decoder then uses this representation to generate the output, say, a translated sentence in French, one token at a time. This setup is perfect for sequence-to-sequence tasks like translation, summarization, and even question answering. T5, for example, is a powerful encoder-decoder model that reframes all tasks as text-to-text transformations. Decoder-only architectures, like the GPT series, are designed for autoregressive text generation. They take an input sequence and predict the next token based only on the tokens that came before. This is achieved using masked self-attention, which prevents the model from cheating by looking ahead during training. Decoder-only models excel at generating coherent, fluent text and are used in applications like chatbots, content generation, and code completion. Encoder-only models like BERT are trained to deeply understand language rather than generate it. They take in the entire input at once and are trained using tasks like masked language modeling, where words are hidden and the model learns to predict them. These models are used for classification, sentiment analysis, and other tasks where understanding is more important than output generation. While they can't write stories or chat fluently, they excel at comprehension and reasoning. Choosing the right architecture depends on your task. If your goal is to transform one piece of text into another, like in translation or summarization, go with encoder-decoder. If you want to generate text from scratch based on a prompt, decoder-only models like GPT are your best bet. For tasks that require analyzing or classifying text without generating new output, encoder-only models like BERT are ideal. Understanding this helps you select the right foundation for building or fine-tuning an LLM for any application. In this session, we'll explore the two most common pre-training strategies for large language models: masked language modeling and causal language modeling. These methods define how a model learns during its initial unsupervised phase, long before any fine-tuning happens. You'll learn how each strategy works, which models use which approach, and how they affect performance on downstream tasks. Understanding MLM and CLM gives you a deeper grasp of why BERT and GPT are so different and how their pre-training shapes their capabilities. Before a language model can be fine-tuned for specific tasks like summarization or sentiment analysis, it first needs to understand how language works. That's the role of pre-training. In this phase, the model is exposed to billions of tokens of raw text and learns to detect patterns, grammar, and semantic relationships without any labeled data. This gives the model a strong foundation that can later be adapted to specialized tasks for supervised fine-tuning. Masked language modeling, or MLM, is a pre-training method where random words in a sentence are replaced with a special token. The model's job is to fill in the blanks using the surrounding context from both the left and the right. This encourages the model to understand relationships across the entire sequence. MLM is used in encoder-only models like BERT, which are designed for comprehension rather than generation. Causal language modeling, or CLM, takes a different approach. The model only sees the tokens that come before the current one and is trained to predict the next word in the sequence. This mirrors the natural process of writing or speaking, where each word builds on the last. CLM uses a left-to-right structure and is foundational for decoder-only models like GPT-2 and GPT-3. It's particularly well-suited for generative tasks like story writing, dialogue, and code completion. The core difference lies in how each model uses context. MLM sees the entire sentence and can reason bidirectionally, making it ideal for tasks like classification or sentence similarity. CLM, by contrast, only looks left and learns to generate coherent sequences, perfect for open-ended generation. The pre-training strategy directly influences what a model is good at. That's why GPT excels at text generation, while BERT dominates in understanding tasks like question answering or text classification. Some newer models combine both strategies to balance understanding and generation. T5, for example, reframes every task, translation, classification, summarization, as a unified text-to-text problem. Its pre-training uses a variant of MLM, but is designed to support both comprehension and generation. The field of pre-training continues to evolve, with new strategies like span prediction, denoising, and contrastive learning entering the picture. What remains constant is that pre-training defines a model's strengths from the very beginning. In this final session of Section 3, we compare three landmark transformer models, BERT, GPT, and T5. You'll learn how their architectures, pre-training strategies, and task orientations differ, and what that means for real-world applications. These models represent the major design philosophies in the LLM ecosystem: understanding with BERT, generation with GPT, and flexible text-to-text tasks with T5. By the end of this session, you'll be able to distinguish their strengths, limitations, and which use cases each one serves best. BERT, GPT, and T5 are foundational models that define how we use transformers in different ways. BERT was designed for understanding, extracting meaning, classifying text, and answering questions. GPT was built for generation, producing fluent, human-like text based on prompts. T5 reimagines everything as a text-to-text task, offering versatility and modularity. Each of these models applies the transformer architecture in its own way to achieve its specific goal. BERT uses an encoder-only architecture, where the full input is processed bidirectionally to capture context. GPT takes the opposite approach, a decoder-only design that processes text left to right for natural generation. T5 combines both, using a full encoder-decoder pipeline, which enables it to reframe every task as input to output text. These architectural choices affect not only how the models are trained, but also what kinds of tasks they're best suited for. Each model also differs in how it learns from data during pre-training. BERT uses masked language modeling. It hides words and trains the model to fill them in using bidirectional context. GPT uses causal language modeling, where each word is predicted from the words before it. T5 uses span corruption, where multiple words are masked together and replaced in a sequence-to-sequence format. These objectives deeply influence how each model generalizes and adapts to downstream tasks. BERT is ideal when you need deep understanding of a passage, like in sentiment analysis, named entity recognition, or classification tasks. GPT shines when you want the model to write, chat, complete code, or generate creative text. T5 offers a middle path. It's great for translation, summarization, and any task that can be cast as text in, text out. Knowing these strengths helps you pick the right model for your workflow or decide which architecture to fine-tune for your use case. Despite their differences, BERT, GPT, and T5 are built on the same foundational blocks: multi-head attention, layer normalization, and position-wise feed-forward layers. What sets them apart are their architectural choices, encoder versus decoder, and how they were trained. These decisions influence their strengths, weaknesses, and intended use cases. Together, these models give us a complete toolkit for understanding and generating language across every domain of NLP. In this session, we'll explore the three most important prompt formats in large language models: zero-shot, few-shot, and chain-of-thought prompting. Each type represents a different level of context provided to the model and serves a distinct purpose. You'll learn when to use each type, how they affect model behavior, and why. Prompt engineering has become a crucial part of deploying generative AI responsibly and effectively. By the end, you'll be able to identify which prompt type fits your task and how to structure it for better results. Prompting is how we communicate with large language models. Instead of writing code, we use carefully worded text to guide the model's behavior. A typical prompt combines a task description, an input, and sometimes additional context or examples. Prompting lets us program the model in natural language, which makes it incredibly powerful and flexible, especially for non-developers. The quality of the output often depends entirely on how well the prompt is designed. Zero-shot prompting is the simplest form of interaction. You give the model a task or question with no examples, and it responds based on what it has learned during pre-training. This approach is fast and requires minimal effort, making it ideal for simple tasks or early experimentation. However, without context or examples, the model may misinterpret the intent or provide less reliable answers, especially on more complex tasks. Few-shot prompting includes a handful of demonstrations before the main task. For example, you might provide 2 or 3 input-output pairs that illustrate how the model should respond. This allows the model to infer the task structure and follow the pattern more reliably. Few-shot prompts are especially helpful for classification, translation, or formatting tasks. The key is selecting clear, representative examples that guide the model without overwhelming it. Chain of thought prompting is designed for tasks that require reasoning, like math problems, logic puzzles, or step-by-step instructions. Instead of just asking for an answer, you guide the model to explain its thinking along the way. This results in more accurate and interpretable outputs. Chain of thought can be used in zero-shot mode, but it's most powerful when combined with few-shot examples. It mimics how humans think through problems and dramatically improves performance on complex reasoning tasks. Each prompting strategy has its strengths. Use zero-shot when you need speed or are still exploring task possibilities. Switch to few-shot when task accuracy matters and examples can clarify the desired behavior. For complex reasoning or multi-step tasks, chain of thought prompting can unlock deeper capability. And don't be afraid to mix strategies. Many high-performing prompts combine elements of all three to maximize performance and reliability.
In this session, we focus on how to craft high-quality prompts that lead to better model outputs. You'll learn best practices like being explicit, controlling tone, using delimiters, and avoiding ambiguity. We'll explore principles that apply to zero-shot, few-shot, and chain-of-thought prompting alike. Whether you're building a chatbot, automating a workflow, or generating structured content, prompt quality plays a critical role. By the end, you'll know how to refine your prompts for clarity, consistency, and task alignment.
Prompt design is not just a technical detail, it's one of the most important factors influencing how well a large language model performs. A well-crafted prompt can produce precise, reliable outputs. A vague or poorly structured prompt often results in confusion or hallucinated content. Like good writing, good prompting takes practice. The encouraging part is that it's highly iterative. You can experiment, test, refine, and quickly see what works. The clearer your prompt, the better the model will respond. Use precise verbs and define the structure of the output explicitly. For example, say, summarize this in 3 bullet points, rather than just, what do you think about this? If you need output in a specific format, like JSON, a table, or a paragraph, state that clearly. Think of yourself as a UX designer for the model. Your prompt is the interface. Adding structure to your prompts using delimiters like triple quotes, XML style tags, or brackets makes a big difference. It signals to the model exactly where the input begins and ends. This becomes especially important in few-shot prompting, where examples must be clearly separated. It also reduces the risk of prompt injection in real-world applications, where users might try to manipulate the model through hidden inputs. Role-based prompting can greatly influence the tone and style of the model's response. By asking the model to act as a tutor, developer, lawyer, or customer support agent, you help it adopt the appropriate language, level of detail, and point of view. This makes your outputs more consistent and aligned with the intended user experience. It's especially useful for conversational agents or task-specific assistants. Prompt engineering isn't a one-shot activity. It's a creative, iterative process. Small wording changes can lead to dramatically different results. Try out multiple prompt versions, compare outputs, and refine over time. Keep logs, test edge cases, and continuously improve. Treat prompting the way you'd treat product UX or design. Each iteration brings you closer to a more reliable and aligned user experience. In this session, we'll examine the concepts of instruction tuning and prompt tuning. two techniques that go beyond basic prompting to improve how large language models understand and execute tasks. Instruction tuning teaches the model how to follow human instructions across many tasks, while prompt tuning creates small trainable prompts that help models generalize without changing their core weights. You'll learn how each method works, when to use them, and how they relate to model alignment and fine-tuning workflows. Instruction tuning is a process where the model is trained on a wide range of tasks, each accompanied by natural language instructions. This allows the model to generalize better and follow directions more reliably, even for tasks it hasn't explicitly seen before. It's what gives models like FLAN T5 and GPT-4 their powerful zero-shot capabilities. Instruction-tuned models are more helpful, versatile, and user-aligned than those trained on raw text alone. In instruction tuning, the model is trained using input-output pairs that look like a user prompt followed by a correct response. For example, translate this sentence to French: I love cats. And the correct answer: j'aime les chats. These examples span dozens of tasks, from question answering to summarization to classification. Over time, the model learns not just the tasks themselves, but how to follow the instructional language that accompanies them. Prompt tuning is a lightweight method for customizing large language models without modifying their core weights. Instead of retraining the entire model, you train a small set of vectors called soft prompts that are prepended to the input. These prompts are not visible to the end user, but influence the model's internal behavior. Prompt tuning is ideal when you want to adapt a large model to a specific task or domain without the expense and risk of full fine-tuning. Although they sound similar, instruction tuning and prompt tuning serve different purposes. Instruction tuning modifies the base model by training on a wide range of labeled tasks. It changes the model's weights. Prompt tuning, on the other hand, adds a trainable layer on top of the frozen model. It's more like attaching a smart lens than retraining the camera. Use instruction tuning when building general-purpose models, and prompt tuning when you need fast, efficient domain adaptation. If you're building or training a general-purpose model to handle a variety of tasks, instruction tuning is the way to go. If you're deploying an existing model to a narrow domain, like legal or medical QA, prompt tuning offers a low-cost, scalable solution. Both techniques can be used alongside few-shot prompting for even better results. Together, they form a powerful toolkit for customizing LLM behavior while preserving performance and alignment. In this session, we focus on one of the most important frontiers in LLM development: model alignment and safety. You'll learn what alignment means in the context of generative AI, why hallucinations occur, and how we mitigate risks through training strategies and prompt design. We'll also explore how reinforcement learning with human feedback, RLHF, plays a role in making models more helpful and less harmful. Whether you're building tools for education, healthcare, or enterprise, understanding alignment is key to responsible AI deployment. Model alignment is about steering the behavior of language models so that their outputs reflect human goals, values, and norms. An aligned model gives useful responses, avoids harmful language, and understands when it doesn't know something. It's not just about accuracy, it's about trust. In real-world deployments, unaligned models can generate toxic content, reinforce bias, or spread misinformation. Alignment is a safety-critical objective that guides how we train, evaluate, and deploy generative AI. Hallucinations are when a language model generates fluent but factually incorrect information. This happens because LLMs are probability machines. They predict the next most likely word based on training data, not actual truth. They may sound confident even when they're wrong. Without external grounding or retrieval mechanisms, models can fill in gaps with made-up details. Hallucinations are especially common in open-ended tasks where precision is not enforced. Alignment starts with supervised fine-tuning, training on datasets curated to avoid harmful, biased, or misleading content. But the real breakthrough came with RLHF, or reinforcement learning with human feedback. This method uses human ratings of model outputs to train a reward model. The LLM is then fine-tuned to optimize for outputs that align with human preferences. This is how models like ChatGPT became more polite, useful, and less likely to say something inappropriate. Prompt engineering is not just about performance, it's also a powerful tool for safety. You can reduce hallucinations and misbehavior by clearly defining the model's role, tone, and boundaries. For example, telling the model you are a factual assistant. Only provide information you are confident in, improve reliability. System-level instructions used in tools like OpenAI's ChatGPT API offer an additional layer of behavioral control. In production, the right prompt can be your first line of defense. Even with the best training and prompting, no model is perfect. That's why alignment also requires rigorous testing. Red teaming is the process of probing a model for failure cases, especially around sensitive topics. Evaluate outputs for toxicity, bias, and factuality using both automated tools and human reviewers. And once the model is live, continue monitoring for new risks. Alignment isn't something you do once. It's a continuous process of evaluation, feedback, and iteration. In this session, we'll compare full model fine-tuning with two increasingly popular alternatives: LoRA, low-rank adaptation, and PEFT, parameter-efficient fine-tuning. These techniques allow developers to adapt large language models without incurring high computational or memory costs. You'll learn what each method is, how it works, and when to use it. By the end of this session, you'll be able to choose the right approach for your use case, whether you're deploying in the cloud, on the edge, or within a highly specific domain. Full fine-tuning involves retraining every parameter of a pre-trained model on new data. This gives you complete control to adapt the model to your needs, but it's computationally expensive. It often requires high-end GPUs, significant memory, and long training times. Full fine-tuning is typically reserved for research labs or enterprise-scale projects with highly specialized data and workflows. It's powerful, but rarely necessary for most practical applications. LoRA, or low-rank adaptation, is a clever technique that allows you to fine-tune a model without touching most of its weights. Instead, it inserts small trainable matrices, called adapters, into specific parts of the network. During training, only these adapters are updated while the rest of the model stays frozen. This dramatically cuts down on memory and compute requirements, making LoRA ideal for tuning massive models like Llama or GPT on consumer-grade hardware. PEFT stands for Parameter Efficient Fine-Tuning, a family of approaches that includes LoRA, prefix tuning, and adapter-based methods. These techniques share one goal: adapt the model to a new task while modifying as few parameters as possible. This is especially useful when you want to specialize a model without losing its general-purpose capabilities. PEFT methods are lightweight, fast to train, and ideal for deployment in edge environments or with limited compute budgets. Each fine-tuning method has trade-offs. Full fine-tuning offers the most flexibility, but it's slow and resource-intensive. LoRA is faster and lighter, offering a good balance between performance and cost. PEFT techniques are the most lightweight. They adapt models quickly using minimal compute, often with just a few megabytes of trainable parameters. The right choice depends on your use case, infrastructure, and deployment needs. If you're deploying a highly customized model for legal, medical, or proprietary workflows, full fine-tuning might be justified. For most cases, LoRA strikes a great balance, especially when adapting foundation models to new prompts or tasks. If you need to build many small models quickly or serve them on edge devices, PEFT is the way to go. All of these methods also play nicely with retrieval augmented generation (RAG) and agentic pipelines, so you can fine-tune your LLM and plug it into a larger system. In this session, you'll get an introduction to NVIDIA NeMo, a powerful end-to-end framework specifically designed for developing and deploying large language models at scale. NeMo simplifies the process of training custom LLMs, fine-tuning existing models, and integrating them into real-world applications. You'll explore its modular design, key components like NeMo Megatron, and its support for multi-GPU and multi-node distributed training. If you're preparing for enterprise-level LLM deployment or research experimentation, NeMo is a key part of the NVIDIA ecosystem you must understand. NeMo is NVIDIA's open-source framework for building, training, and deploying large-scale AI models, especially language models. It's built to handle everything from model design to training and real-time inference. NeMo is optimized for GPU acceleration and multi-node setups, making it ideal for enterprise and research environments. Whether you're working on text generation, speech recognition, or multi-model tasks, NeMo offers tools to move from idea to deployment fast. NeMo comes with a rich library of pre-trained models, including GPT, BERT, T5, and more. These models can be fine-tuned on your own data or extended for new tasks. Its modular design means you can mix and match components like tokenizers, encoders, and decoders to build your own architectures. One of its most powerful features is support for Megatron LM, which enables model parallelism, splitting very large models across multiple GPUs or nodes for faster and more efficient training. The NeMo Megatron toolkit is what allows NeMo to scale to truly massive model sizes. Think hundreds of billions or even trillions of parameters. It implements sophisticated forms of parallelism, data, tensor, and pipeline to maximize GPU utilization. This is the same technology NVIDIA uses to train its own foundational models. It also supports mixed precision training, reducing memory usage while maintaining accuracy and speed. NeMo is ideal when you're building LLMs for specific domains like healthcare, finance, or legal. It simplifies both the training and fine-tuning pipelines while integrating seamlessly with other NVIDIA components like Triton Inference Server and TensorRT. If you're deploying on DGX hardware or within an enterprise cloud setup, NeMo ensures scalability, performance, and maintainability. It's a full-stack framework for real-world LLM development. You can get started with NeMo in just a few steps, install it via pip, or pull pre-built containers from NVIDIA NGC. There are excellent tutorials covering text classification, summarization, ASR, and more. Most workflows use PyTorch Lightning and Hydra for configuration, so it's easy to tweak experiments and scale up. Whether you're working on a laptop or a cluster, NeMo is designed to get you building fast. In this session, we'll explore Triton Inference Server, NVIDIA's high-performance model deployment platform designed to serve AI models at scale. You'll learn how Triton handles model loading, batching, scaling, and deployment across GPUs and CPUs. We'll cover its support for multi-framework inference, performance optimization techniques like dynamic batching, and how it integrates with LLMs and enterprise systems. Triton is essential for taking your fine-tuned models for research to production, especially in latency-sensitive or large-scale environments. Triton Inference Server is NVIDIA's open-source platform for deploying AI models in production. It supports a wide range of model formats, ONNX, TensorFlow, PyTorch, and even custom backends like JAX. Triton is optimized for multi-GPU and multi-model workloads, so you can serve many models from a single instance. It integrates with enterprise tools like Kubernetes, Prometheus, and Grafana, making it ideal for scalable, production-grade AI services. Triton is built with speed and flexibility in mind. It enables dynamic batching to improve throughput, allowing it to group incoming requests before processing them on the GPU. You can run models concurrently and across different hardware, manage multiple versions of a model, or even chain models together using ensemble execution. It provides both gRPC and HTTP endpoints, so integrating into your app or service is straightforward. With LLMs becoming increasingly large and powerful, Triton provides the infrastructure needed to serve them efficiently. You can deploy NeMo-tuned or Hugging Face-based models into Triton containers, running them on multi-GPU hardware with support for auto-scaling and intelligent load balancing. Whether you're delivering real-time chat responses or batch document summarization. Triton ensures your LLM inference is fast, reliable, and resource efficient. Triton uses a centralized model repository structure to manage your models and their configurations. Each model can have multiple versions, useful for A/B testing, rollback, or iterative development. Configurations are defined using simple JSON files, which include model input-output specs, batching rules, and optimization settings. You can update models on the fly, making Triton a flexible and production-hardened choice for LLM deployment. To ensure your deployed models run at peak performance, Triton offers built-in observability features. You can export metrics to Prometheus and visualize them in Grafana, enabling real-time monitoring of GPU usage, latency, and throughput. Triton also supports auto-scaling in Kubernetes clusters, so you can expand or shrink resources based on demand. With profiling tools and dynamic batching, you're always in control of cost and performance. In this session, we explore NVIDIA Rapids, a powerful suite of open-source libraries for GPU-accelerated data science and machine learning. You'll discover how Rapids leverages GPUs to replace traditional CPU-bound workflows in Python using tools like cuDF for data frames and cuML for classical ML algorithms. We'll also compare Rapids with Pandas and scikit-learn and look at how it integrates into LLM pipelines for pre-processing and tabular reasoning tasks. If you want to eliminate data bottlenecks and accelerate pipelines before they reach your LLM, Rapids is essential. Rapids is NVIDIA's open-source framework for building GPU-accelerated data pipelines using familiar Python syntax. It includes drop-in replacements for common CPU-bound tools like Pandas, NumPy, and scikit-learn. Under the hood, Rapids uses CUDA to speed up computation dramatically, but exposes a Python API, so data scientists don't need to learn low-level GPU programming. It's designed to scale across multiple GPUs and large datasets, eliminating the CPU bottlenecks in traditional ML and LLM pipelines. cuDF is the Rapids GPU-accelerated version of Pandas. It provides nearly the same syntax, so you can switch with minimal code changes, but with huge performance gains. cuDF shines when dealing with large tabular data, especially for pre-processing steps like filtering, encoding, and joining. It's a perfect fit for LLM workflows that require structured data inputs, such as CSV ingestion or feature engineering, before generating natural language responses. cuML is a GPU-powered library for classical machine learning. It replicates many scikit-learn functions, including linear models, clustering, PCA, and random forests, but runs entirely on the GPU. It works hand-in-hand with cuDF and integrates into Rapids pipelines, enabling fast experimentation and production-ready ML components. For example, you can pre-process tabular data with cuDF and run PCA or k-means directly using cuML before feeding results into an LLM or model ensemble. In an LLM workflow, data preprocessing can be a major bottleneck. Rapids solves this by allowing you to parse and clean CSV, JSON, or Parquet files at GPU speed using cuDF. You can structure and segment your input with cuML models, then send it to Triton for inference, or integrate with NeMo for real-time AI pipelines. Whether you're preparing financial statements, user logs, or survey data for analysis, Rapids brings efficiency and scale. The performance difference between CPU-based tools and Rapids can be massive. While Pandas and scikit-learn are familiar and reliable, they can become slow and memory-intensive with large data sets. Rapids offers GPU-accelerated performance with minimal code changes, enabling you to process, model, and infer data 10 to 50 times faster. If your LLM application involves heavy data wrangling, switching to Rapids can make the difference between waiting minutes and getting results in seconds. In this session, we focus on NVIDIA TensorRT, the ONNX model format, and how model optimization enables faster, more efficient AI inference. You'll learn how these tools reduce latency, shrink model size, and boost throughput, critical when deploying large models like GPT or BERT in production. We'll explore the conversion process, quantization, precision tuning, FP32, FP16, INT8, and how these fit into enterprise pipelines. If your goal is to run AI workloads cost-effectively at scale, Mastering these tools is essential. TensorRT is NVIDIA's deep learning inference optimizer and runtime. It's designed to maximize performance and minimize latency when running AI models on NVIDIA GPUs. TensorRT can take models from PyTorch, TensorFlow, or OwnNX and compile them into highly efficient execution graphs. Whether you're deploying to edge devices or data center GPUs, TensorRT ensures your models run as fast and lean as possible. OwnNX, short for Open Neural Network Exchange, is a framework-neutral format for representing AI models. It lets you train a model in one framework, like PyTorch, and deploy it elsewhere, such as with TensorRT or Triton. OwnNX is essential for model portability, particularly when you need to deploy across different environments. It serves as the bridge between research and production, making hardware acceleration tools like TensorRT accessible regardless of your training platform. Optimization is about making your models smaller, faster, and more GPU-friendly. TensorRT achieves this through techniques like layer fusion, which combines operations for efficiency, and kernel auto-tuning, which finds the best execution path. It also supports reduced precision, using FP16 or INT8 instead of FP32 to drastically lower memory usage and boost speed. With dynamic shape support and graph pruning, TensorRT tailors each model for real-time deployment without sacrificing accuracy. To use TensorRT, start by exporting your model, either directly to OwnNX or using tracing tools for PyTorch. Then, you can invoke the TensorRT command line interface or Python APIs to compile and optimize the model. For INT8 precision, you'll run a calibration step using sample data. Finally, validate that your optimized model matches the original in accuracy. This workflow turns high memory, high latency models into deployable assets, fast, lean, and production ready. In the LLM pipeline, optimization sits between fine-tuning and deployment. Once your model is trained, perhaps using NeMo or Hugging Face, you export it to OwnNX. From there, TensorRT can optimize it for inference, ensuring minimal latency and GPU load. You can then serve the model through Triton Inference Server in production. You'll deploy it to an edge device like NVIDIA Jetson. This workflow unlocks massive speedups, lower costs, and greater responsiveness for your LLM-based applications. In this session, we explore NVIDIA DGX systems, purpose-built AI supercomputers, and Base Command, the software stack that manages training jobs, resource scheduling, and multi-user workflows. You'll learn how DGX enables large-scale LLM training with extreme performance and parallelism, while Base Command provides researchers and engineers with a powerful command center for distributed AI development. Whether you're building trillion parameter models or running collaborative LLM experiments in the cloud, this section ties the full NVIDIA ecosystem together. DGX systems are NVIDIA's flagship AI supercomputers. They're purpose-built for high-performance AI training, especially workloads like deep learning and large language model development. These systems pack multiple A100 or H100 GPUs and use NVIDIA NVLink and NVSwitch technologies to create ultra-fast communication between GPUs. That's critical for parallelizing LLM training across billions of parameters. If you're scaling from research to enterprise-grade AI, DGX is the gold standard in infrastructure. LLMs are compute-intensive and require powerful hardware to trade efficiently. DGX systems are optimized for exactly this kind of workload. They offer high throughput for data ingestion, fast checkpointing to disk, and full support for mixed precision training, using FP16 or BF16 to save memory and speed up computation. DGX also integrates deeply with the NVIDIA software ecosystem, giving teams a validated, production-ready environment for scaling up LLM training. Base Command is the orchestration platform that runs on top of DGX infrastructure. Think of it as mission control for your AI experiments. It provides a clean web interface and CLI tools to schedule jobs, track performance, and share environments across teams. Researchers can submit training jobs, monitor GPU usage in real time, and retrieve logs, all from one central place. For large teams working on parallel LLM experiments, Base Command is essential for coordination and visibility. Not every team can host DGX machines on-prem. That's where DGX Cloud comes in. NVIDIA partners with cloud providers like Azure, Oracle, and Google Cloud to offer DGX systems on demand. You get the same performance, same tooling, but no hardware to manage. The base command platform supports hybrid workflows, mixing on-premise and cloud resources, so you can scale up your LLM development with agility, whether it's a short-term spike or ongoing research. DGX Cloud has you covered. DGX and Base Command are the backbone of NVIDIA's LLM stack. You train massive models with NeMo on DGX, manage runs in teams with Base Command, and then optimize your models using TensorRT. Once ready, you serve the models through Triton Inference Server or NVIDIA AI enterprise tools. It's an integrated pipeline from infrastructure to inference, engineered for scale, speed, and reliability. In this session, we'll focus on how to prepare raw data for large language models through pre-processing and feature engineering. This is a foundational step for any LLM pipeline. You'll learn techniques to clean, normalize, and transform data, how to handle missing or noisy text, and how feature engineering extends beyond tabular data into token-level processing and enrichment. Whether you're training from scratch, fine-tuning, or doing retrieval-augmented generation, RAG, effective preprocessing significantly impacts model performance and robustness. Data preprocessing is the first and most critical step in any LLM workflow. If the input data is messy, inconsistent, or poorly structured, even the best model will struggle. Models are only as good as the data they're trained or fine-tuned on. Noise, duplicate content, or malformed tokens can cause hallucinations or unpredictable outputs. Thoughtful preprocessing ensures the model receives clean, contextually coherent inputs, leading to more stable, useful results. Preprocessing begins with simple but powerful text cleaning techniques, lowercasing text, removing punctuation or HTML tags, and collapsing extra whitespace. You'll also want to remove links, emojis, or language artifacts depending on your task. Identifying and filtering out non-target languages can further boost performance in monolingual settings. Deduplication and enforcing a reasonable maximum length per example are also common practices, especially important for batching and consistent tokenization. Different tasks call for different pre-processing strategies. If you're building a summarization model, you might need to remove extraneous headers and footers. For question answering, it's crucial to correctly extract and pair questions with their answers. In chat datasets, you may need to strict timestamps or usernames, which could otherwise bias the model. And for retrieval-based systems, you'll want to chunk and tag documents with relevant metadata for downstream indexing. In traditional ML, feature engineering involves creating new variables. In LLMs, this translates into injecting structure into the text. For example, you can tag different speakers in a transcript, append control tokens to steer output behavior, or use labeled prompts to teach new tasks. In a few-shot setting, how you craft and format the examples. Your prompt engineering is also a form of feature design. It's all about helping the model understand context better through structure. Thankfully, you don't need to build everything from scratch. Libraries like Spacy, NLTK, and simple Python regex are powerful for cleaning and filtering. LangChain helps structure data for retrieval workflows. Hugging Face datasets makes it easy to load and map functions over large corpora. And if you're working at scale, Rated's cuDF lets you process massive tabular or mixed format datasets directly on the GPU, perfect for speeding up pipelines before model ingestion. In this session, we'll explore how LLMs transform text into machine-readable formats through tokenization and embeddings. You'll learn how text is broken down into subwords or tokens, and how each token is mapped to a dense vector, an embedding that captures meaning, context, and relationships. We'll also examine common tokenization schemes like byte pair encoding, BPE, and sentence piece, how embeddings evolve during training, and how pre-trained embeddings can be used or fine-tuned. Understanding this process is foundational for building better prompts, improving memory efficiency, and debugging model behavior.
Tokenization is the process of splitting text into smaller units, called tokens, that a model can work with. These tokens might be full words, subwords, or even individual characters, depending on the tokenizer used. For example, the word unbelievable might be broken into un, believe, and able by a subword tokenizer. This step is essential because models can't operate on raw text. They need a way to turn language into numbers. And tokens are the first step in that transformation.
There are several types of tokenizers, and each affects how efficiently a model can process language. Byte pair encoding, BPE, merges the most common character pairs into subwords. Word keys, used in BERT, optimizes the vocabulary to reduce token sequence lengths. Sentence piece tokenizes without needing pre-tokenized text and is commonly used in multilingual models. The tokenizer you choose can affect model speed, memory usage, and how well it handles rare or compound words. Once the text is tokenized, each token is mapped to an embedding, a dense vector that represents its meaning. These embeddings are like coordinates in a high-dimensional space where similar words or phrases cluster together. They're learned during training, so the model develops an internal understanding of language. For example, embeddings for Paris and London might be closer together than Paris and carrot, because the model learns they're both cities. Transformers don't process sequences like humans do. They need to be told the order of tokens explicitly. That's where positional embeddings come in. They're added to token embeddings to encode the position of each word in a sequence. Segment embeddings, on the other hand, are used to distinguish parts of the input, for instance, the question versus the answer in a Q&A task. Together, these allow the model to understand not just the meaning of tokens, but also their arrangement and role in the input. Embeddings aren't just for model inputs, they're incredibly useful on their own. You can use them for similarity searches, clustering, or even to feed into vector databases like FACE or Pinecone. Visualizing embeddings can help detect bias, concept drift, or outliers. When fine-tuning a model, you may choose to update just the embeddings while freezing other weights. And if you're working with APIs like OpenAI or NeMo, you can generate embeddings directly from your LLM for downstream tasks like classification or semantic search. In this session, we'll examine how large language models are evaluated using quantitative metrics like BLEU, Rouge, and Perplexity. You'll learn what these scores actually measure, how they're calculated, and when to use them. We'll also discuss their limitations, especially in creative or open-ended tasks, and how human-in-the-loop evaluations often complement automated metrics. Understanding evaluation is crucial for comparing models, iterating on prompt designs, and validating the effectiveness of fine-tuning strategies. Evaluating a large language model is just as important as training or deploying it. Without objective metrics, it's impossible to tell whether a model is improving, regressing, or producing better outputs for specific tasks. Evaluation allows us to validate prompt effectiveness, compare models, and ensure our models meet user expectations. It also keeps experimentation scientific and repeatable. BLEU, or Bilingual Evaluation Under Study, is one of the oldest metrics for evaluating text generation. It's commonly used in machine translation and measures how much of the model's output overlaps with a human reference, focusing on exact n-gram matches. Higher BLEU scores indicate greater similarity, though perfect matches aren't always required. BLEU is great for narrow, high-precision tasks, but less suited for creative or open-ended generation. Rouge, which stands for Recall-Oriented Understudy for gisting evaluation, is another popular metric, especially for summarization. Unlike BLEU, Rouge emphasizes how much of the reference text the model captures, measuring recall. It includes variations like Rouge N for n-gram recall and Rouge L for longest common subsequence. A high Rouge score means the model output contains many of the key ideas found in the reference. Perplexity is a fundamental metric for language models that aren't yet deployed. It measures how confidently the model predicts each next word in a sequence. Lower perplexity means the model is less surprised by the correct continuation, indicating more fluent language generation. However, perplexity doesn't always align with downstream performance. It tells us how well the model fits data. not whether the output is useful or relevant to a specific task. Despite their utility, traditional metrics like blue and rouge have limitations. They reward surface level similarity, so diverse but valid outputs may get penalized. For open ended tasks like storytelling, reasoning, or coding, human evaluation remains essential. Newer approaches like BERT score and Comet use embeddings to evaluate meaning instead of words, and some researchers now even use other LLMs to evaluate LLMs. Ultimately, a mix of metrics and human judgment leads to the best insights. In this session, we'll cover the vital practice of experiment tracking and reproducibility in LLM development. As language models become larger and more complex, keeping track of changes in datasets, hyperparameters, prompts, and outputs becomes essential. You'll learn about tools that log every run, techniques to ensure experiments are repeatable, and why this discipline is crucial for scaling research, collaboration, and model validation. Whether you're a solo practitioner or part of a large team, tracking and reproducibility are the foundation of trustworthy AI. Experiment tracking isn't just about staying organized, it's about making sure your work leads to reliable outcomes. Without tracking, you may repeat past mistakes, lose valuable configurations, or forget what worked. By logging parameters, datasets, code versions, and outcomes, you create a traceable workflow. This allows you to compare models objectively, debug with clarity, and share results with your team or stakeholders confidently. For an LLM experiment to be reproducible, you need to capture the full context of what was run. That includes the version of the dataset and how it was cleaned, the model architecture and checkpoint used, and any prompt design or tuning strategy applied. Just as important are the results, evaluation scores, logs, and outputs. When all of this is documented, another team member, or your future you, can rerun the same experiment and get consistent results. Thankfully, you don't have to build your own tracking system. Weights and biases is a popular choice with visual dashboards and real-time logging. MLflow provides model versioning and even lets you deploy models from its registry. TensorBoard is commonly used in TensorFlow projects for visualizing metrics like loss curves. And if you're in the NVIDIA ecosystem, Base Command offers integrated experiment tracking across DGX nodes. These tools make tracking both efficient and insightful. True reproducibility requires more than just logging metrics. It's about recreating the full environment. Always fix random seeds for libraries like NumPy, PyTorch, and transformers. Use containers like Docker or environments like Conda to ensure dependencies stay the same. Save configuration files and scripts with each run, and version your code and data using tools like Git and DVC. These habits help you future-proof your work and collaborate without confusion. Beyond personal benefit, experiment tracking ensures your work can be transferred, audited, and trusted. In larger teams, it supports knowledge sharing and project continuity. In regulated industries like finance, government, or healthcare, maintaining logs of every experiment is often a compliance requirement. Reproducibility isn't just good science, it's good business, especially as AI governance becomes mainstream. In this session, we'll explore how to scale large language models from experimentation to production with optimal performance and GPU efficiency. You'll learn strategies for high-throughput inference, batching, quantization, and model parallelism. We'll also discuss how to monitor GPU memory and utilization, handle latency-sensitive workloads, and architect scalable pipelines using tools like Triton Inference Server and TensorRT. Whether you're running models on a laptop or across DGX clusters, understanding performance engineering is key to maximizing value from LLMs. Large language models are computationally expensive. Even after training, running them at scale, whether for chatbots or batch tasks, requires serious infrastructure. You have to manage GPU memory, reduce inference latency, and maintain high throughput. This introduces trade-offs. Smaller models are faster, but may be less accurate. Batching increases efficiency, but adds complexity. Scaling isn't just about hardware, it's about smart design. There are several proven ways to speed up inference. Batching multiple requests together helps maximize GPU use. Mixed precision inference using FP16 or BF16 reduces memory usage while keeping performance high. Quantization takes it a step further, converting weights to INT8 to speed up calculations even more. And profiling tools can reveal bottlenecks you didn't know existed. Together, these tactics turn slow, expensive models into production-ready engines. NVIDIA provides powerful tools to get your model ready for production. TensorRT compiles and optimizes models specifically for GPU inference, often boosting performance by 2 to 6 times. Triton Inference Server can run multiple models concurrently with GPU-aware scheduling and load balancing. If you're transferring between platforms, OnNX provides a universal format. And with NeMo, you can export ready-to-serve models that plug straight into optimized infrastructure. What's deployed? It's critical to monitor how your GPUs are being used. Tools like NVIDIA SMI and DCGM show memory usage, active processes, and even thermostats. You want to ensure your models aren't idling too long, consuming excess memory, or underutilizing expensive hardware. When paired with auto-scaling strategies, these metrics help right-size your infrastructure, keeping costs low and performance high. Scaling isn't just about model speed, it's about system architecture. You might deploy multiple inference endpoints behind a load balancer to serve global users. For really large models, you'll use model parallelism, splitting layers across GPUs, or pipeline parallelism, chaining different parts of the model. Async APIs with retry logic help smooth spikes in demand. With the right patterns, your LLMs can go from proof of concept to robust, scalable services. In this final stretch, we turn theory into practice. This session focuses on simulating full-length mock exams to build your endurance, confidence, and timing strategy for the actual NCA-GENL certification. You'll learn how to structure practice sessions, analyze results, and develop strategies for time management, focus, and error reduction. Mock exams aren't just for testing your knowledge, they're your dress rehearsal for game day. The better you simulate the pressure, the better you'll perform when it matters most. Mock exams are more than just practice. They're your opportunity to test your readiness in real exam conditions. They help uncover which topics still need attention and expose patterns in how you manage time or handle tricky questions. Just like an athlete needs scrimmage games before a tournament, mock exams build the stamina and pacing strategy you'll need to succeed on the actual test. To get the most out of your mock exams, mirror the real NCA-GENL format. 60 multiple-choice questions over 90 minutes. Pull questions across all key domains: model architecture, prompt engineering, optimization, evaluation, and NVIDIA tooling. Remove distractions, time yourself strictly, and note which questions you guessed or flagged. The goal is to replicate the pressure, not just review material passively. One of the biggest challenges in the exam is time pressure. Aim to spend no more than 90 seconds per question. If you get stuck, don't spiral. Mark it and come back. Use checkpoints. For example, after 20 questions, see if you're on track time-wise. In mock exams, train to finish with a few minutes to spare, allowing a sanity check at the end. Time discipline often matters more than perfect answers. After each mock exam, don't just glance at the score. Analyze it. Where are you consistently making mistakes? Are you second-guessing correct answers? Are certain question types like prompt tuning or evaluation metrics tripping you up? Tracking performance trends lets you focus your final review on the areas that will bring the biggest score improvements. In your final prep week, aim for 2 or 3 full mock exams. Don't cram them all back to back. Space them out so you can review each one thoroughly. Within 24 hours of each exam, revisit every wrong answer and understand why you missed it. Use this cycle: exam, review, reinforce, to lock in your final gains. Combine mocks with flashcard bursts or short topic reviews to reinforce the trickiest concepts. In this session, we shift from learning new content to sharpening what you already know. Mistake analysis helps uncover not just what went wrong, but why. You'll learn how to categorize errors: conceptual, strategic, or careless, and how to tailor your last mile review to address them. We'll also go over high-yield review techniques that consolidate your strengths and patch your weaknesses. This is where elite test takers separate themselves through focused correction and smart final sprints. Every wrong answer is a signal. Was it a lack of understanding, a misread question, or a moment of doubt? Mistake analysis goes beyond correcting answers. It reveals how your brain is handling the exam under pressure. This helps you address not just gaps in content, but flaws in reasoning or time use. In this phase, mistakes are your best teachers. Not all mistakes are created equal. Conceptual errors mean you need a review, maybe around transformer layers or alignment techniques. Strategic errors come from using the wrong approach, like choosing fine-tuning when LoRA was better. Careless mistakes often stem from fatigue or speed. And sometimes you had the right instinct but changed your answer. Understanding what kind of mistake you made lets you fix the root cause. Build your own mistake journal. Use a simple spreadsheet or a digital notebook like Notion to log every missed question. Note the topic, what went wrong, and what the correct reasoning should have been. Over time, you'll see clusters, maybe a recurring issue with model serving or prompt types. In the final week, this log becomes your go-to review guide, more valuable than any course or textbook. Last mile review is about precision, not volume. Go back to your flashcards or cheat sheets. Run mini drills, just 10 to 15 questions on your weakest sections. Teaching a concept aloud, even to yourself, forces clarity. And make sure you revisit any MCQs that stumped you before. The goal now is reinforcement, not exploration. In your final 24 hours, your job is to stay calm and trust your preparation. Light review is fine, but don't cram. It'll spike your anxiety. If anything, do a short quiz in the morning as a warm-up. Visualize success. You know what to expect. You've seen the traps. You've trained for this. Use a pre-exam ritual, whether it's music, meditation, or affirmations, to bring your mind into peak state. In this session, we'll compile your final checklist of NVIDIA tools, frameworks, and skills that may appear in the NCA-GENL exam. This is not about theory anymore. It's about being ready to act. Whether it's recalling how to serve an LLM with Triton Inference server, export a model from NeMo, or choose between LoRA and fine-tuning, this section brings it all together. We'll walk through hands-on skills you should have practiced and give you a last chance readiness scan to make sure you're prepared on every front, mental, technical, and strategic. Let's start with your toolkit. You should feel confident using NeMo to train, fine-tune, and export models. You should understand Triton Inference Server's role in scaling inference. TensorRT is key for optimizing and quantizing models, especially for deployment. SuDF and SuML help with fast data wrangling. And if you're in the enterprise space, knowing what NVIDIA DGX and Base Command offer is critical for LLM scalability. At this point, you should have gone beyond watching videos. You should have done the thing. Whether that's tokenizing data with QDF, running a prompt-tuned model in a Jupyter notebook, or writing a config for Triton, your fingers should have touched the code. Even if the exam itself is multiple choice, the confidence that comes from real-world practice will show up in your answers. It helps to consolidate the critical commands and concepts on one cheat sheet. Know your CLI commands, NVIDIA SMI to monitor usage, TRTXEC to test models, 1B to track experiments. Be able to read or recognize Python snippets from NeMo for tasks like model export or prompt tuning. Understand when to use LoRA versus PEFT versus full fine-tuning. Review the math behind metrics like perplexity or BLEU one last time. These are the high-yield details that could tip the balance on a few tough questions. If you still have time, consider doing a quick end-to-end pipeline. Load a model, run it on a dataset, serve it with Triton, and evaluate with BLEU or Rouge. Even just going through the motions will solidify muscle memory. Try tweaking PEF configs or tracking token throughput in a deployment setting. These aren't mandatory, but if you want to feel rock solid on exam day, hands-on review is a great way to get there. You've done the learning, you've done the labs, but now comes one of the most overlooked parts of exam success: making sure your test environment is set up and your mind is ready. This session focuses on the practical logistics of taking the NVIDIA-Certified Associate exam in a remotely proctored setting. We'll walk through technical setup, system requirements, do's and don'ts during the exam, and how to avoid common pitfalls that can result in disqualification. The final hour is not the time for surprises, so let's get it right. The NCA-GENL exam is delivered online, but under strict proctoring rules. You'll be monitored via your webcam, microphone, and screen sharing. That means no books, phones, or dual monitors. A valid government-issued photo ID is required to verify your identity. And the entire session, from login to final submission, is recorded. It's a real exam environment, even from home. Before test day, confirm that your system meets technical requirements. A reliable internet connection is critical. Dropouts can disrupt or void your session. Your webcam and mic should be working, and you'll need a quiet, distraction-free space. Use a modern browser like Chrome and turn off anything that could interfere. Notifications, antivirus pop-ups, or scheduled restarts. Run a system check at least a day in advance. On the day of the exam, give yourself a buffer. Restart your system an hour before to ensure updates don't kick in. Join the exam 15 to 20 minutes early to complete ID verification and system checks. Keep your ID ready for the camera and close every application except the exam platform. If you can, have a backup hotspot or network option in case Wi-Fi fails mid-exam. During the exam, your behavior is monitored closely. Looking away, whispering, or leaving your seat can trigger a flag or even invalidate your attempt. Avoid talking to yourself. Keep your face in the frame and don't shuffle around unnecessarily. Some proctors may intervene if they see suspicious behavior, so it's best to be calm, still, and focused the entire time. If anything unexpected happens, like a power cut, internet drop, or browser crash, stay calm. Most remote proctoring platforms have an in-exam chat feature to speak with support. Document any error with screenshots. In most cases, you'll be able to reschedule or resume. If the session cannot continue, reach out to NVIDIA's certification support team with details. You've prepared too hard to let a technical issue stop you, so have a plan just in case. Even the best prepared candidates can falter without the right mindset. This final session is your mental warm-up. We'll go beyond technical skills to focus on confidence, clarity, and composure. You'll learn how to manage exam day nerves, reinforce belief in your readiness, and shift from passive anxiety to active self-assurance. The mindset you bring into the exam room can raise or lower your score. Let's make sure yours is strong, focused, and ready to win. Confidence isn't something you either have or don't. It's something you build. You studied, you've practiced, and you've earned the right to be confident. Nervousness is just excitement with a little doubt. Flip that energy. Visualize success. See yourself answering calmly, solving tricky questions, finishing strong, and be kind to yourself. If doubt creeps in, respond like a coach, not a critic. Anxiety is natural, but manageable. Deep breathing slows your heart rate and clears your mind. Stay tall or sit up straight. Your posture affects your mental state. If allowed, sip water to reset your nerves. And most of all, accept the pressure. It means you care. A bit of adrenaline can sharpen focus. You don't have to eliminate discomfort. Just channel it. Small rituals have a big impact. Wear something comfortable and familiar. Play music that energizes or centers you. Repeat affirmations. I am prepared. I am capable. I trust my training. These cues signal to your brain that it's time to perform. Avoid last-minute cramming. It creates panic, not preparation. Stick to your system and walk in with calm resolve. Every test taker hits a wall at some point. If that happens, don't spiral. Take 3 deep breaths. If a question stumps you, mark it and move on. Use easier questions to rebuild your rhythm. Momentum is powerful. And remember, one tough question doesn't define your score. Each question is a new opportunity. Regain control one click at a time. When you enter that exam room, virtual or physical, Carry the mindset that you've already won. You've done the work. This is just the final step in showcasing your knowledge. Stay in the moment. Don't worry about the score. Focus on each question as it comes. And when you hit submit, do it with pride. You didn't just prepare for an exam, you leveled up as a professional.